Hello, and welcome to this video on Computer-Aided Drug Delivery System, or CADDs. This lecture is presented by Dr. Krishna Yadav, and this is Unit 3, Part 1 of the M-Pharm Pharmaceutics curriculum, Semester 2. We begin with Chapter 1, Introduction to Computer-Aided Formulation Development, or CAFD, focusing on formulation development and pharmaceutical optimization. Chapter 2 covers the fundamental concepts and parameters of optimization. Optimization is defined as finding the most effective variable values to achieve a specific objective, subject to defined constraints. Optimization in pharmaceutical formulation is the scientific process of identifying the most favorable combination of formulation variables to achieve desired properties. It forms the backbone of modern rational drug product development, moving beyond time-consuming trial and error. Traditional empirical observation, or trial and error, is time-consuming, requires high material consumption, and is highly resource-intensive. CAFD, or systematic optimization, helps reduce development timelines, minimizes material use, and ensures a robust and reproducible final product. The theoretical framework of optimization involves the objective function, seeking the global maximum or minimum of f of x by finding the variable vector x. Optimization algorithms include gradient descent for convex problems and genetic algorithms for nonlinear responses. A primary limitation is that results can be mathematical artifacts if the model is poor. Optimization parameters are classified as independent variables, or factors you control, and dependent variables, the measurable outcomes, or critical quality attributes, or CQAs. Independent variables are the knobs, denoted as X, while dependent variables are the responses, denoted as Y. This table summarizes the classification of optimization parameters, including their notation, action, and examples. Independent variables include formulation and process examples, while dependent variables include physiochemical and biological or PK examples, the CQAs you measure. Parameters can have quantitative or continuous numerical levels, or qualitative or categorical levels. The curse of dimensionality shows that the number of required experiments, or runs, explodes exponentially with the number of factors, k. Constraints are the limitations or boundaries placed on variables, such as maximum surfactant concentration or minimum drug content, ensuring the formulation is feasible. Design space is the multi-dimensional combination of input variables that assures quality, defined by overlaying contour plots where all constraints are satisfied. This diagram illustrates the concept of defining constraints. The red areas are outside the feasible solution space, or the design space. The boundaries are mathematical inequalities that truncate the theoretical response surface, ensuring safety and manufacturability. The knobs and dials metaphor defines the anatomy of an equation. Y equals f of x plus epsilon. X represents the independent variables, or the knobs you turn. F of x is the function, the mathematical engine. Y represents the dependent variables, or the CQAs you measure. Epsilon is the unexplained variance. Factorial design is the most widely used experimental design in pharmaceutical optimization. It allows for the simultaneous investigation of multiple factors and their interactions in a structured manner. A factorial design investigates all combinations of factor levels. In a full factorial design, if there are k factors, each with n levels, the total number of experiments required is n to the power of k. For a two-level, two-factor design, 4 experiments cover all combinations, typically coded as -1 and +1. This example of a 2 to the power of 3 full factorial design shows the 8 experimental runs required for 3 factors at 2 levels. This design allows estimation of all main effects and interaction effects. The detailed steps illustrate the process from selection to analysis and optimization. A 3-squared full factorial design studies 2 factors, each at 3 levels, requiring 9 runs. It enables the estimation of all main effects and 2-factor interactions, providing a reliable model for optimization. For a 3-cubed factorial design with 3 factors at 3 levels, 27 runs are required. This design estimates all main effects, 2-factor interactions, and the 3-factor interaction, and is balanced and orthogonal. Fractional factorial design is used when the number of factors is large, as full factorial becomes resource prohibitive. A 2 to the power of k minus p design uses fewer experiments, but higher-order interactions become confounded with lower-order ones. In the fractional factorial design notation, 2 to the power of k minus p, k is the total number of factors, and p is the degree of fractionation, indicating how much the full factorial design is reduced. Aliasing or confounding occurs when 2 or more effects are mathematically indistinguishable because the design doesn't allow for their separate estimation. This loss of information happens when you drop runs from the full factorial design. This image illustrates the concepts of resolution and alias structure in fractional factorial designs, which are key characteristics when designing and interpreting these experiments. Moving on to the effects calculated in factorial design, we consider main effects, interaction effects, and statistical significance. Main effects measure the average effect of a single factor on the response. Interaction effects measure the non-additive influence of 2 or more factors. The significance of these effects is tested using the p-value in ANOVA. Response surface methodology, or RSM, is an extension of factorial design that fits a second-order polynomial model to account for the curvature typically found in pharmaceutical systems. This is vital for quality by design, or QBD, for establishing design space and finding the optimum. The image highlights the key characteristics of response surface methodology, including its goal to determine the optimum, its reliance on a second-order polynomial model to capture curvature, and its foundation in the design of experiments. RSM is based on a second-order polynomial equation, which includes linear terms, 2-factor interaction terms, and quadratic terms, allowing it to capture the nonlinear relationship between factors and responses. Common RSM designs include central composite design, which uses factorial, star, and center points, Box-Benken design, a 3-level design without corner experiments, and optimal designs, which are computer-generated to maximize information from limited runs. This image compares the 3 most common response surface methodology designs, visually illustrating the placement of design points for central composite design, Box-Benken design, and D-optimal design. The selection of the appropriate design depends on the number of factors, the complexity of the response surface, and resource constraints, balancing the need for comprehensive data with experimental feasibility. Optimization technology includes computational methods and algorithms for solving formulation optimization problems. Major technologies include classical optimization, Lagrangian method, linear programming, canonical analysis, artificial neural networks, genetic algorithms, and the desirability function. These will be covered in next videos. This video concludes with the references used in the development of this Unit 3 Part 1 module on computer-aided formulation development and optimization.